So I'm going to tell you about some experiments I've done in James's group on this thing called quantum simulation. And if you're not a physicist, you might not know what this phrase means. If I ask you to describe it, you might imagine something vaguely blue and sci-fi-y, like DALL-E apparently does, which is trained on the median image in the data set. And apparently quantum simulation is a bunch of floating orbs around a giant wavy sphere thing. Um, yeah, so to be clear, this is not what I do, but the fact that this is kind of a hokey, wavy sounding phrase means that I should probably start by introducing what we mean by quantum simulation, and hopefully also by the time I'm done, you'll also walk away knowing why we care, why these are important experiments to run. And to start with that, let's consider some everyday object, like an apple. It might seem pretty simple on its surface, but if you peer back beneath the layers, you'll find that there's millions of plant cells inside. Inside those plant cells are organelles, and in those organelles are a bunch of molecules that interact, et cetera, et cetera. It's turtles, right, all the way down. And so you might look at this system and say, well, if even the simplest of things has all this complexity, how do we know anything about anything? And the answer, of course, is that none of this information is really relevant most of the time when you're trying to predict the behavior of a system. If I take this apple and I go to the top of the Gila Tower and try to kick it off, do we need to know how many cells are inside this apple? Not really, right? All we really need to know is that it's this point mass that's going to fall under gravity. And so we come up with a simple model of the apple, and we predict that if we kick that point mass, it's going to undergo some parabolic arc and fall to the ground. So this is kind of how we understand a lot of complex systems in science. But making the model is only the first step of this two-step program. The second step is we have to actually test the predictions of that model. We could pretend the apple is anything we want, but if it doesn't reflect reality, it's not that useful. So I go up to the top of the Gila Tower and I run a fake experiment where I kick the apple off the top. And we see that, yeah, qualitatively, the apple follows the predictions of our model pretty well. So that's a success for the model. Now, it's not perfect. If we want to quantitatively make predictions about this, we might want to introduce additional layers of complexity, like air resistance in this case. And you can keep going with adding more layers of complexity to your desired level of precision. But this gets you most of the way there. This is kind of a contrived experiment, but we can port that philosophy to a system that physicists care about a lot, which is superconductivity. So this is kind of a strange state of matter. It's a little bit like a metal, except it has almost zero electrical resistance. And moreover, it has this weird effect called the Meissner effect, which means it repels magnetic field lines, allowing you to make these fun pictures of superconductors floating over magnets. Now, these two properties are really desirable from an engineering standpoint, and so we would really like to understand why superconductivity happens in this system so we can make more and better versions of them. But because it's a complex system, we need to come up with some simple model that maybe describes the essential physics. And so step one of our two-step program is come up with the model. Some smart people in the 50s came up with this, the BCS model, which without going into too much detail, basically describes how electrons gain some effective interaction by talking to phonons in the lattice in the middle. And somehow that generates superconductivity. So that's step one. Step two of the program is try to test this model's predictions. And people have done this with various types of metals, like aluminum and lead, now called conventional superconductors. And people actually saw it. Yeah, actually, the BCS model qualitatively describes these systems quite well. And that won Bardeen, Cooper, and Schrieffer the Nobel Prize in 1972. But sort of a decade later, people discovered a whole new class of materials called unconventional superconductors. And they're called that because they're not well described by the BCS model. And so we kind of have to come up with a new simple model that describes the essential physics. So let's start this two-step program over again. This time, the simple model for unconventional superconductivity, a good candidate is this Fermi-Hubbard model, which, again, without going into much detail, basically describes how electrons gain some Cooper pairing through spin fluctuations in the lattice. Okay, we have a simple model. Does it describe reality? We have to test the model's predictions. And this is where we start to run into problems. The issue is that even though the Fermi-Hubbard model is simple to set up, it's very computationally expensive and difficult to generate predictions of the model. This here is a proposed phase diagram of this model, which has a superconducting region. But the phase boundaries of this phase diagram, we don't really know that precisely. We don't know exactly where they're supposed to be. And if we can't generate predictions, we can't test to see if it reflects reality. So what do we do? Are we doomed forever? Not really. To understand what our next steps are, I'm going to take a really brief tangent into a completely unrelated system to hopefully draw inspiration, which is the San Francisco Bay. So I'm not from the Bay Area, but I've been a few times. The Bay is beautiful. It's a very complex ecosystem too, with a bunch of endangered species. But this bay in its current form would not exist if it were up to this guy by the name of John Reber from the early 20th century, who looked at this and saw not a beautiful ecosystem, but a geographic mistake. In his view, the bay was an impediment to efficient urban planning and led for inefficient road design and stuff. And so his proposal to fix this, called the Reber Plan, was to dam up most of the bay, build 20,000 acres worth of military installations, and a 32-lane highway from SF to Oakland. So it was even controversial at the time, but there was actually a lot of appeal to this program in the zeitgeist of the times, at least. And part of the appeal was John Reber's claim that damming up the bay would generate freshwater lakes in the dammed up sections, which would provide a nearly unlimited source of water for an area that was already starting to experience water issues. The issue is that John Reber was not an expert or an engineer. He was an actor, actually. And but moreover, even professional engineers disagreed on whether his plan would work the way he claimed. Now, if this were the present day, you could set up some numerical simulation and compute what happens when you put these dams in. But this was the 1930s. They didn't have computers. So just like in our case with the superconductor, they didn't have the computational resources to solve this problem. Instead of giving up, what we did was we had the US Army Corps of Engineers build a full giant replica of the entire San Francisco Bay, which you can still see in Marin County today, by the way. And so the idea is, if they physically put in some dams and analogly simulate this model, they could test whether his predictions work or not. So they did this, and sure enough, they found that the plan would have been a total economic and ecological disaster, effectively killing Reber's plan. But this is just a good example of how when the government funds rigorous scientific studies to inform government policy over the opinions of some non-experts, you can win. But the real moral of the story for this talk is that if you can't calculate a model, maybe you can build it instead. And that's exactly what we're going to do with quantum simulation. If we return to our Fermi-Hubbard model, remember, we can't compute this model's predictions because it's too hard. So one thing we can try instead is to literally build an analog version of this model using atoms and test out what's supposed to happen. And that is what we're trying to do with quantum simulation, or analog quantum simulation. Predict the behavior of quantum models by building them directly.